Representation corruption is when data no longer means what it was supposed to mean, not because assumptions changed, but because the representation itself was damaged. A useful metaphor for representation corruption is a scratched vinyl record. The music is still there in theory, but physical damage introduces noise, skips, and distortions. The playback system follows the rules correctly, yet the output is wrong because the medium itself is corrupted. Representation corruption works the same way in data systems. So what is representation corruption? Representation corruption occurs when the encoded form of data is altered in an unintended way, causing the decoded meaning to diverge from the original reality. Unlike drift, corruption is not about evolving meaning. It is about broken encoding. Corruption changes bits, bytes, symbols, or structures so that the representation no longer faithfully encodes the intended value. How does representation corruption occur? Corruption can happen at many layers of a system. At the hardware level, memory cells can flip bits due to cosmic rays, heat, or aging components. Storage media can degrade, sectors can fail, and transmission channels can introduce errors. At the software level, bugs can write incorrect values, truncate buffers, misalign structures, or violate invariants. Serialization bugs can reorder fields, drop bytes, or misinterpret types. At the system level, concurrency issues, partial writes, crashes, and network interruptions can leave data in inconsistent states. Corruption can also occur through human error, manual edits, misconfigured pipelines, incorrect migrations, or flawed transformations can inject invalid representations into otherwise valid datasets. Why do systems experience representation corruption? Because every layer in a data system is imperfect. Bits are physical. Software is written by humans. Networks are unreliable. Storage devices fail. Systems crash. Representation corruption is the cost of building systems in the physical world. Even with checksums, redundancy, and validation, corruption cannot be fully eliminated. It can only be mitigated and detected. Representation corruption has several defining features. First, it is localized. A single bit flip can change a number, a character, or an entire structure. Second, it is often invisible. Corrupted data may still pass correctly and pass schema validation. Third, it is non-semantic. The corruption does not respect meaning. It produces arbitrary errors rather than systematic shifts. Fourth, it is irreversible without redundancy. Once the original bits are lost, the true value cannot be reconstructed unless backups or error-correcting codes exist. Finally, corruption is stochastic. It does not follow predictable patterns and may appear sporadically. The implications of representation corruption are severe. In databases, corruption can break indexes, violate constraints, and cause silent data loss. In analytics, corrupted records distort aggregates and bias results, especially when errors are rare but extreme. In machine learning, corrupted labels or features poison training data and degrade model performance in unpredictable ways. In distributed systems, corruption can cause replicas to diverge, protocols to fail, and state machines to enter invalid states. In safety-critical systems, representation corruption can lead to incorrect control decisions with physical consequences. Representation corruption undermines the fundamental premise of data systems, that stored and transmitted symbols correspond to reality. Because corruption is arbitrary, it is often harder to reason about than drift or truncation. Professional systems treat corruption as a first-class threat. They use checksums, cryptographic hashes, error-correcting codes, redundancy, replication, journaling, and transactional semantics. They validate invariants, monitor anomalies, and perform audits and reconciliation. They assume that any component can fail and that any stored bit may eventually flip. Because representation corruption is not an edge case. It is an inevitability. And in data systems, trust is built not by assuming representations are perfect, but by designing systems that survive when they are not.